Okay, hi everyone, welcome back to the Comptia Security Plus course. RC. RC stands for different things depending on who you talk to. Officially it's known as Rivest Cipher, but is playfully known as Ron's code as well. There are multiple RC versions, most of which are not related, aside from the fact that they are all encryption algorithms. RC4 is somewhat widely used stream cipher in protocols such as SSL, WEP and RDP. It is known for its speed and simplicity. However, it is avoided when designing newer applications and technologies due to several vulnerabilities. When used with WEP on wireless networks, it can be cracked quickly with the use of aircrack PTW. One way to avoid this to a certain extent is to use the Temporal Key Integrity Protocol TKIP with WEP. However, it is still recommended that AES and WPA2 be used in wireless networks. Some versions of Microsoft Remote Desktop Services use RC4 128-bit. However, Microsoft recommends disabling RC4 if at all possible and using other encryption such as Federal Information Processing Standard FIPS compliant encryption, IPsec and EFS and TLS for authenticating. RC5 is a block cipher noted for its simplicity and for its variable size -32, -64, 128-bit. The strongest RC5 block cipher that has been cracked via brute force as of the writing of this book is a 64-bit RC key in 2001. This was done by Distributed.net, a non-profit organization which at the time had 30 TFLOPS of computational power. It is also working on cracking the 72-bit version of RC5 with substantially higher output at its disposal. This is a cause for concern for some because Moore's law tells us of the effective doubling of CPU power every 2 years or so, but you must remember that stronger algorithms such as AES 256-bit are exceptionally hard to crack. RC6 is a block cipher entered into the AES competition and was one of the 5 finalists. Though it was not selected, it is a patented algorithm offered by RSA Security as an alternative to AES. It is similar to AES in block size and key size options, but uses different mathematical methods than Ringdell. Blowfish and Twofish. Blowfish and Twofish are two ciphers designed by Bruce Schneider. The original Blowfish is a block cipher designed as an alternative to DES. The name also pertains to a suite of products. It has a 64-bit block size and variable key size between 32 and 448 bits. Bruce Schneider recommends the newer Twofish cipher, which has a block size of 128 bits and a key size up to 256 bits and is also based on Fiestel. There is also a newer Threefish block cipher with key sizes up to 124 bit. These symmetrical ciphers have not been compromised, but they do have minor weaknesses that can be exploited by birthday attacks and key separation. Summary of symmetric algorithms. Table 14.3 gives some comparisons of the algorithms up to this point and their key size. Key size is the number of bits in a cipher. It is also referred to as key length or key strength. DES data encryption standard 56-bit. 3DES triple DES 168-bit. AES advanced encryption standard 256-bit. RC4 Rivest Cipher version 4 128-bit typical. RC5 Rivest Cipher version 64-bit typical. RC6 Rivest Cipher version 6 256-bit typical. Twofish 128-bit, 192-bit, 256-bit. RSA, the original and very common RSA, which stands for Rivest, Shamir and Edelman, the creators, is a public key cryptography algorithm. As long as the proper size keys are used, it is considered to be a secure protocol and is used in many e-commerce scenarios. It is slower than symmetric key algorithms but has advantages of being suitable for signing and for encryption. It works well with credit card security and TLS SSL. Key lengths for RSA are much longer than in symmetric crypto systems. For example, 512-bit RSA keys have proven to be breakable over a decade ago. However, 1024-bit keys are currently considered unbreakable by most known technologies, but RSA still recommends using the longer 248-bit key, which should deter even the most powerful super hackers. It is important to note that asymmetric algorithm keys need to be much larger than their symmetric key counterparts to be effective. For example, 128-bit symmetric key is essentially equal to a 2304-bit asymmetric key in strength. The RSA algorithm uses what is known as integer factorization cryptography. It works by first multiplying two distinct prime numbers that cannot be factored. Then it moves on to some more advanced math in order to derive a set of two numbers. Finally, from these two numbers, it creates a private and public key pair. The private key is used to decrypt data that has been encrypted with the public key. For example, if Alice user A sends Bob user B a message, Alice can find out Bob's public key from a central source and encrypt a message to Bob using Bob's public key. When Bob receives it, he decrypts it with his private key. Bob can also authenticate himself to Alice, for example, by using his private key to encrypt a digital certificate. When Alice receives it, she can use his public key to decrypt it. These concepts are summarized in table 14.4. Task: which person's key to use, what kind of key. Send an encrypted message, receiver's public key. Decrypt an encrypted message, receiver's private key. Send an encrypted signature, sender's private key. Decrypt an encrypted signature's, sender's public key. Other examples of RSA encryption include tokens in the form of secure ID, USB dongles and devices such as hardware security modules, HSMS, and trusted platform modules, TPMs. All these devices can store RSA asymmetric keys and can be used to assist in user authentication. RSA key distribution is vulnerable to man-in-the-middle attacks. However, these attacks are defensible through the use of digital certificates and other parts of a PKI system that we detail in the next chapter. It is also susceptible to timing attacks that can be defended against through the use of cryptographic blinding. This blind computation provides encryption without knowing actual input or output information. Due to other types of attacks, it is recommended that a secure padding scheme be used. Padding schemes work differently depending on the type of cryptography. In public key cryptography, padding is the addition of random material to a message to be sufficient and incorporating a proof, making it more difficult to crack. A padding scheme is always involved, and algorithm makers such as RSA are always releasing improved versions. In 2000, RSA Security released the RSA algorithm to the public. Therefore, no licensing fees are required if an organization decides to use or modify the algorithm. RSA published a group of standards known as PKCS, Public Key Cryptography Standards, in an effort to promote its various public key techniques. For example, PKCS 1 defines the mathematical properties of RSA, public and private keys. Another example is PKCS 11, which defines how HSMS utilizes RSA. The entire list of standards can be found at the following link. Diffie-Hellman. The Diffie-Hellman key exchange, invented in the 1970s, was the first practical method for establishing a shared secret key over an unprotected communications channel. This asymmetric algorithm was developed shortly before the original RSA algorithm. It is also known as the Diffie-Hellman Merkle key exchange due to Ralph Merkle's conceptual involvement. Diffie-Hellman relies on secure key exchange before data can be transferred. This key exchange establishes a shared secret that can be used for secret communications, but over a public network. Originally, fictitious names were chosen for the users. Alice and Bob. Basically, Alice and Bob agree to initial prime and base numbers. Then each of them selects secret integers and sends an equation based on those to each other. Each of them computes the other's equation to complete the shared secret, which then allows the encrypted data to be transmitted. The secret integers are discarded at the end of the session. These were originally static keys, meaning that they were used for a long period of time. Diffie-Hellman is considered secure against eavesdroppers due to its difficulty of mathematically solving the Diffie-Hellman problem. However, it is vulnerable to man-in-the-middle attacks. To prevent this, some method of authentication is used, such as password authentication. This algorithm is used by the Transport Layer Security (TLS) protocol during encrypted web sessions. When used in this manner, it works in imperial mode, meaning that keys are generated during each portion of the key establishment process and are used for shorter periods of time than with static keys. It is this ephemeral process that achieves perfect forward secrecy (PFS), which ensures that the compromise of the message will not lead to the compromise of another message. The imperial version of Diffie-Hellman is called DHE, or sometimes Imperial Diffie-Hellman EDH, because it uses an imperial key, meaning that the cryptographic key is generated for each execution of the key establishment process. One of the drawbacks of DHE is that it requires more computational power. However, there is an elliptic curve alternative, which we talk about in the next section. Elliptic curve. Elliptic curve cryptography (ECC) is a type of public key cryptography based on the structure of the elliptic curve. It uses algorithms calculated against a finite field and is based on the difficulty of certain mathematical problems. It uses smaller keys than most other encryption methods. Keys are created by graphic specific points on the curve, which are generated mathematically. All parties involved must agree on the elements that define the curve. this asymmetric algorithm has a compact design, leading to a reduced computational power compared to other asymmetric algorithms, yet it creates keys that are difficult to crack. Other algorithms have been adopted to work with elliptic curves, including Diffie-Hellman and the digital signature algorithm, DSA. The Diffie-Hellman version, known as Elliptic Curve Diffie-Hellman or ECDH, uses elliptic curve public-private key pairs to establish the secret key. Another variant, elliptic curve Diffie-Hellman Imperial ECDHE, runs in imperial mode, which as previously stated makes sure that a compromised message won't start a chain reaction and other messages maintain their integrity. By its very design, the elliptic curve solves the problem of the extra computational power required by DHE. DSA is a US federal government standard public key encryption algorithm used in digital signatures. The elliptic curve, known as as ECDSA, in general, the size of the public key in an elliptic curve based algorithm can be 1/6 the size of the elliptic curve version. For example, ECDSA has a public key that is 160 bits, but regular DSA uses a public key that is 1024 bits. This is part of the reasoning behind the reduced amount of CPU power needed. ECC is used with smart cards, wireless security and other communications such as VoIP and IPsec. With DSA, it can be susceptible to side channel attacks, SCAS, which are attacks based on leaked information gained from the physical implementation, number and types of curves of the crypto system, and fault attacks, a type of SCA. Plus, there are concerns about backdoors into the algorithm's random generator, elliptic curve cryptography, as well as RSA and other algorithms, is also theoretically vulnerable to quantum cryptanalysis based computing attacks. More encryption types. We have a couple of more encryption types to speak of. They don't quite fit into the other sections, so I figured I would place them here. The first one is one-time pad and the second is PGP, pretty good privacy application and encryption method. One-time pad, also known as the Vernam cipher, named after the engineer Gilbert Vernam, is a stream cipher that encrypts plain text with a secret random key that is the same length as the plain text. It uses a string of bits that is generated. A random, known as a key stream encryption, is accomplished by combining the key stream with the plain text message using the bitwise XOR operator to produce the ciphertext. Because this key stream is randomized, even an attacker with a plethora of computational resources on hand can only guess the plain text if the attacker sees the ciphertext. Unlike other encryption types, it can be computed by hand with a pencil and paper, thus the word pad in the name. Although today's computers will be used to create a one-time pad algorithm with the use of technology, it has proven as impossible to crack if used correctly, and is known as being information theoretically secure. It is the only crypto system with theoretically perfect secrecy. This means that it provides no information about the original message to a person trying to decrypt it illegitimately. However, with this type of encryption have stopped from being widely used. Because of this, the acronym OTP is more commonly associated with one-time passwords, which we talk about later in this chapter. One of the issues with a one-time pad is that it requires perfect randomness. The problem with computer-based random number generators is that they usually aren't truly random, because high-quality random numbers are difficult to generate. Instead, they are pseudo-random number generators, PRNGs, discussed a bit later. Another issue is that the exchange of the one-time pad must be equal to the length of the message. It also requires proper disposal, which is difficult due to data remnants. Regardless of these issues, the one-time pad can be useful in scenarios in which two users in a secure environment are required to also communicate with each other from two other separate secure environments. The one-time pad is also used in proper encryption or multi-encryption, which is encrypting an already encrypted message. In addition, it is commonly used in quantum cryptography, which uses quantum mechanics to guarantee secure communications. These last two concepts are far beyond the Security Plus exam, but they show the actual purpose for this encryption type. So I'm going to leave this video here today. If you like listening, please consider like, sharing and subscribing. Thank you.